So we started talking about Hawking radiation. We're going to finish Hawking radiation today, I think. So this is the eternal Schwarzschild black hole. That is the maximal analytic extension of the Schwarzschild metric. This is not what actual black holes look like, but that's okay. And our strategy is going to be as follows. First, we're going to define a state called the Hartle-Hawking state. By a Euclidean path integral. Similar to how we talk about the Minkowski vacuum as being given by Euclidean path integral, but it's a little different because this is just going to be a definition. I'm just going to define it by a Euclidean path integral, as opposed to the Minkowski vacuum, which is the lowest energy state. We derived the fact that the Minkowski vacuum was this path integral. So we're just going to define it. That state is going to be defined, well, I don't know if this is a step or just an observation, but rho A is thermal in the Hartle-Hawking state. And in step 3, we're going to show that this is relevant to real black holes, that is, black holes that form by collapse. Okay, so I just want to make the logic clear, so it's clear what's the definition and where the physics is coming in. Okay, so we're going to start with step 1. We're going to define a state by a Euclidean path integral. The path integral, what we're going to do is we're going to take the Schwarzschild metric here. Oh, you're trying to get the lights? I think I have to turn these on. There we go. Yeah, so we're gonna analytically continue this metric here to get the Euclidean black hole, and we're gonna do the path integral on the Euclidean black hole. That's gonna be our definition of the Hartle-Hawking state. Okay, so let me start by describing this Euclidean black hole. Okay, so we just take the metric, the Schwarzschild metric, and take t to I tau, and that gives us the Euclidean metric. So let's write it down again. It's ds squared is 1 minus 2m over r, d tau squared, plus dr squared over 1 minus 2m over r, plus r squared d omega squared. And we're going to identify tau as a circle of size 8 pi m. Why is that? Well, we checked last time that near the horizon, the Schwarzschild metric near the horizon is Rindler space. And Rindler space had an imaginary time identification. So if we want to write down a smooth Euclidean manifold, we have to make this identification. We have no choice. We described it last time in Lorentzian signature, but you could redo this now just using this Euclidean metric, just expand near the horizon and check that there's no conical defect there. And you'll find that you must make this identification. Okay, so now what I want to do is draw this. Okay, I can only draw 2 dimensions. I can't draw 4, but you can imagine the other 2. So to draw this, let's start near the horizon. That is for r near 2m. For r near 2m, we derived the metric last time. And it was r squared d a to e squared plus dr squared. So what we actually did last time was the Lorentzian one, and so this had a minus sign. But now I've just rotated to Euclidean. There were some rescalings involved to get from this metric to that one. If you do it in this coordinate system, actually I didn't write it down in this coordinate system, so I won't be able to get the coefficients easily, but it's going to be similar. It's just going to be well, let me just draw a picture of it instead of writing a formula because I don't have the coefficients. So it just looks like a plane. And the point r equals 2m is the origin in polar coordinates. So that's a point. And tau is identified. So tau is the, so r is the radial coordinate, and tau is the angular coordinate up to this factor of 4 pi m or whatever. So the horizon, r equals 2m, is the origin of this coordinate system. And what I'm drawing here is just a little patch of the Euclidean black hole near the horizon. Yes?
This might be a dumb question, but I never understood something. When we do the t goes to I tau, is that a change of variables? In the sense we have a real t-axis and we say, okay, now this is I tau, or are we saying the t variables are complex, so it's a t in the real axis, and also a complex part tau?
You should not think of it as a change of variables, but as an analytic continuation. And what I mean by that is the following. Okay, so if we have we start with a line, t. Okay, there's the line, t. I'm not going to draw the extra directions. Okay, we start with a line, t. And this is what a line looks like, so there it is. And when we take t to I tau, what we're really doing is we're now thinking about, we're now going to the complex plane, and we're thinking about the other axis. Okay, so there's a complexified geometry, which is this whole plane, and it has an extra dimension. But the usual Schwarzschild metric is this piece of the t-plane, and the Euclidean Schwarzschild metric is this piece of the t-plane, and they meet at a point in the middle. So it's not that we're putting a different coordinate on the same manifold, it's that we're now talking about this other manifold that is this slice of the picture. Does that answer your question?
Yes, so this metric happens at t equals 0, basically.
Well, yeah, but then you have to go out in this other direction.
Because it goes in tau instead of t.
Yeah.
Okay.
Yeah. On this picture, the Euclidean manifold comes out.
Perfect. Thank you.
Other questions? Okay, so that's just a little patch near the horizon. Now, if we go far away from the black hole, that is r much bigger than m, then what does this metric look like? At large r, the first term is just d tau squared, and this is just dr squared. Okay, so so far away, it just looks flat, but tau is identified. Okay, so this metric here is a cylinder. This is the metric of a cylinder. It looks like this. Where tau goes this way, and r goes that way. Okay, so what does it look like everywhere? Now we can draw the manifold. We could do this carefully by looking at the geometry everywhere, but it's sort of obvious what the answer has to be. So let me make r go out this way. Okay, so far away, it's going to be a cylinder. But when r gets to 2m, that has to be the origin in polar coordinates. Okay, so that means it's a cigar. I don't know why this is called a cigar. It's a ridiculous name for it. It's always called the cigar geometry, though. I can't help it. Okay, so this is, I didn't draw it very well.
Who came up with it for the first time?
What?
Who came up for it for the first time and when?
I don't know. I don't know. They were calling it this a long time ago, but I don't know who came up with it. Okay, so r equals 2m is this point here. So if we look locally around this point, then it agrees with our picture for the near horizon. So r equals m is like, or sorry, r equals, well, when you get to r is a few times m, or a few times 2m, it turns into a cylinder. Okay, so basically as you go out, you're getting further away from the black hole, and then r is just becoming the cylinder coordinate, and tau is the coordinate that goes around. So this is called a cigar. Now, let's go back to the Lorentzian. Let's ask how this is related to the Lorentzian manifold that we started with. Okay, so, well, if we set t to 0, that's the same as tau equals 0. And remember, we started in Schwarzschild coordinates, which cover this patch here. Okay, so the region, this line here, which I'll put a squiggle, is shared by the Euclidean and Lorentzian manifolds. This is just like that picture on the t-plane I was drawing a minute ago. So this is t equals 0, so it should be the line tau equals 0 on this picture. Okay, so let's put that here. Okay, so that's region A. It goes out to infinity, and it ends at the horizon. So this point here, which is called the Euclidean Horizon, is the point at the middle of the Penrose stack. notice that a couple things. One is that Euclidean horizons have one less dimension than Lorentzian horizons. So the Lorentzian horizon is this whole thing, but the Euclidean horizon is just this point. The other thing to notice is that Lorentzian black holes have interiors. This region, this sort of mysterious region inside the black hole. And Euclidean black holes do not. There is no inside of a Euclidean black hole. There is no, like, past the horizon of a Euclidean black hole. When you get to the horizon, that's just the origin in polar coordinates, and if you keep going, you don't end up inside the black hole. Yeah.
Could you explain why we chose the origin to be 2m? Why is that the origin in polar coordinates?
Oh, so in the Euclidean metric, we showed last time that if you, well, you can't take r less than 2m because it'll go singular, but we showed last time that if you expand for r near 2m, then this piece of the metric just looks like polar coordinates.
And why is the origin at r? Because you, I guess I'm confused why you cut it off at r equals 2m.
Well, big R equals 0 is the origin in polar coordinates, right? But if you track back the coordinate changes that we did last time, big R equals 0 is little r equals 2m. So that's that point on the manifold. Yeah.
So the black hole doesn't have an interior in Euclidean signature, but isn't that just an artifact of the fact that we started in short-shield coordinates instead of like classical coordinates or something?
No. No. The Euclidean manifold is
Right, but we could have started with some other coordinates, like critical coordinates, and then like analytically continue a different coordinate in that to become imaginary.
Yeah, actually, if we did that in classical coordinates, I don't think you would get a real metric by doing that. And I don't think there's any other reasonable, real Euclidean metric that you could get starting from short shield, no matter what coordinate system you picked.
Why is that?
Well, in Kruskal, the reason it won't work in Kruskal is because the Kruskal time, which goes up, is not an isometry of this manifold. So you'll have explicit t's appearing in the metric, and when you take t to it, you'll have i's in the metric, and you won't really get a Euclidean manifold. Yep.
Oh, can we minus y symmetric singular when r is more than 2m? It seems it's still regular, although it has a strange signature.
Yeah, if you take r less than 2m, then this is a weird but smooth manifold. But that manifold is not connected to this one. Like this manifold just closes off, and there's like nowhere else to go when we get to r equals 2m. So we never talk about the r less than 2m version of this metric.
I would guess that it probably prepares the state in the interior, but which is not the case here.
Oh, that other manifold?
Yeah.
I have no idea what that manifold does. I don't think it prepares a state in the interior because this is not the time direction in the interior. This is the time direction in the interior, and this is I don't know of any use of that manifold. There may be some use of that manifold, but I've never seen it used for anything. Okay, so there's another piece of this picture that we need to fill in, which is what happened, where this part fits in. Okay, so there's region B. Okay, so region B on the left is also on the Euclidean manifold. Now, this is not obvious. This is not obvious because we started out with coordinates on this patch, But I claim that region B is what you get on the other side of the cylinder. Okay, so if you go along region A, you get to the horizon, and then you keep going onto the other side. I claim that's region B. Now, how do I know that? Because of Rindler space. Okay, if you remember, if you go back to our discussion of Rindler, we had Minkowski, and then we discussed how Rindler is sort of, well, if you go to polar coordinates, sorry, if you go to Euclidean, that comes out. So there's a Euclidean thing coming out this way. And then Rindler was like the polar coordinates on the Euclidean manifold. So in Rindler, if you go around by pi, you end up on the other side of Minkowski space. So if you go around by pi, you end up on the other side. Well, we've already seen that the Euclidean black hole is just Rindler near the horizon. So the same thing is true here. If we're right near the horizon here, and we go around by pi in the Rindler coordinate, halfway around the thermal circle, then we're going to end up on the other side. So that's what this picture is saying. It's saying that the whole size of this circle is 8 pi m, but there's a slice at tau equals 0, which is A, and there's this other slice on the other side at 4 pi m, halfway around, and that's the other asymptotic region of the black hole. Yeah.
So B, the region B doesn't exist in Schwarzschild coordinates.
Correct. It's not covered by Schwarzschild.
So by going to the complex plane, you're kind of turning around and going to the extended Schwarzschild.
Yeah, that's right.
Okay.
We can go around. It's a lot like this. It's that in Euclidean we can get around to the other Schwarzschild patch. And I'm about to try to draw the Euclidean manifold coming out here, but it's going to mess up my picture because it's hard to draw. But really, you could think of it the same way: is that Euclidean manifold? Well, let me go ahead and draw it. I'm going to do this in 2 steps. First, I'm just going to flatten the picture. Okay, what do I mean by flatten the picture? I'm just going to flatten the cylinder like this. Squish. All right, so if we squish the cylinder, then now it looks like this. R goes out. Region A is on one side, and region B is on the other side. Okay, so I'm just redrawing it. This is just a redrawing of the cylinder, so you should think of, so in this picture, this was like an accurate picture. This was a geometrically accurate picture of the manifold. This is the actual shape that this manifold has. This has the right topology, but it does not have the right metric. Okay, so this picture, you have to think of this disk as having some funny metric on it to account for the fact that it's really shaped like a cylinder. But I can draw it this way. And the way to think about these pictures is that the Lorentzian and Euclidean manifold are related if we take this Euclidean manifold, turn it sideways, and then attach it over on here. Let me say that again. Take this Euclidean manifold, turn it sideways, and then patch together regions A and B. Okay, so there's a disk coming out of the board and going also behind the board, and that's the Euclidean manifold. Then it's clear why this point in the center of the Penrose diagram is the origin in polar coordinates, right? Okay, so maybe I won't try to draw it. It's going to mess up my pretty pictures. There's a disk. Just imagine the Euclidean manifold. Okay, is that clear?
And then the rest of the cigar comes like out in some sense because up is like imaginary T and like out is like tau.
No, the radial, this direction, the radial direction on the cigar,
Yeah.
is the radial direction on that disk.
Yeah, I just mean like the other like length piece.
No, going out along the length is coming out onto the disk.
Okay. And then how is moving in tau?
So moving in tau, like let's, for example, let's draw a path on here. Where'd my marker go? Okay. So let's start in the middle of region A and go around the tau circle. Okay, so we go onto the other side, we hit region B, and then we end up back at the point we started. So what is that on this picture? You're starting halfway in region A, and then you're going around the angular direction of the disk to here. You hit point B, and then you keep going on the other into the board and back around to the point you started. Other questions? Yeah.
Why did you flatten the cigar first before placing it?
Otherwise, it's very hard to put on here. I can't put it on here. Yeah. So it's the disc. There's this disc coming out. Oh no, I draw it. Okay. There's a disc coming out, but there's a funny metric on the disc. The disc has a cigar metric. So that's the way to think. Yeah. Was there a question? No. Yes.
Yeah, so like instead of choosing the origin to be 2m, I choose something greater than 2m. So then I would have to also continue to r less than 0.
You mean if you just did a coordinate change?
Yeah.
Yeah. If you did a shift of the r coordinate, then you would find the origin is somewhere else. It's not at 0, it's somewhere else.
No, I mean like, instead of choosing the origin to be at r equal to 2m, maybe I
Well,
choose
sorry,
r
we-
equal to 4m.
Well, depends what you mean by choosing the origin. Okay, this point here, we don't have any choice about where that point is. That point is determined geometrically by saying that this is the point where the tau circle shrinks to 0.
Yeah.
Okay, so this point is not a coordinate choice. It's the point where the tau circle shrinks to 0.
Oh.
Yeah, we're not picking it. It was forced on us by the shrinking of the tau circle. Other questions? Okay. So far I've described the Euclidean manifold. And now we can implement the strategy I outlined to define a quantum state. So the path integral on the cigar defines the Hartle-Hawking state. The Hartle-Hawking state is this. Okay, so let me explain what this is. This is the cigar using the flattened picture. It's the cigar using, it's the path integral on the half cigar using the flattened picture. If I didn't flatten it, then it would look, I don't know if I can draw this. Let's see if I can draw it. It would look something like that. Where this is A and this is B. So this state lives in the Hilbert space that is associated to the full region, A union B, or you could say the product Hilbert space HA times HB. It's the state on the full space that goes all the way across the black hole onto both sides. In particular, it's pure. We can write down a formula for this state. Using the same tricks we were using before to talk about the Unruly effect, Unruly radiation. Okay, so let's write down a formula. So this is at tau equals, this is tau equals 0, and tau is the angular direction, and this is halfway around the circle, so it's at tau equals 4 pi m. Therefore, the Hartle-Hawking state is exactly the thermal field double state that we define at inverse temperature 8 pi m. Remember that the thermal field double was defined by doing the path integral well, when we did Rindler, it was exactly the same path integral, just the coordinates were different. It was exactly the same. Okay, so for exactly the same reason here, this is, again, preparing the thermal field double state on the union of A and B. Yeah?
Yeah, so thermal field double with respect to the generator of like translations in tau.
Correct. So, that's important. So this is the thermal field double with respect to d by d tau. The conserved charge associated to tau translations, and this is a crucial point. The conserved charge associated to tau translations is the ordinary Hamiltonian. Because tau is just Euclidean time. It's not so say we live far away from the black hole. Our time coordinate is t. So that's our proper time coordinate. And so we measure energy, for example, with respect to the Schwarzschild t coordinate. That's an inertial observer far from the black hole, uses the Schwarzschild t coordinate. And the conserved charge of our thermal field double is with respect to that coordinate. Okay, so this is the ordinary energy. Where by ordinary energy, I mean for an inertial observer far away. Well, in Euclidean, so the Euclidean translation is by tau, but when you go to Lorentzian, that becomes t. But the conserved charge the conserved charge is the same whether you call it t or tau. We checked that for Rindler. So when we were doing Rindler, we said that there was an e to the minus beta h in Euclidean, or sorry, it was in that case it was q of d theta, and then we checked that there were two i's involved in the Wick rotation to get back to Lorentzian, and this turned into the ordinary Hamiltonian for time translations, Rindler time translations in that case. But now it's just the ordinary, truly the usual Hamiltonian.
Sorry, but in that case, we got the accelerated Hamiltonian. So the K, Hamiltonian of the
That's right.
accelerated.
In that case, it was the accelerated one. But what I mean is the i's went away when we
Yes.
Wick rotated.
So in
Yeah.
that case, rotating in Euclidean gave a charge that was the energy measured by an accelerated observer. But
Yes.
in this case, it's the Hamiltonian of an inertial observer at infinity, like it's a normal observer, or it's accelerated somehow.
Just sorry, by inertial, I really mean fixed r. And
So he's accelerating.
no, fixed r away because in Schwarzschild coordinates, fixed r when r is large is at rest.
Okay.
You don't, in other words, in order to sit 1,000,000 miles away from a Schwarzschild black hole, you do not require a rocket booster, unlike the situation in Rindler. This is really an ordinary observer.
That's an approximate statement that becomes true as we take r to infinity.
Right, that's right. Yeah. Yeah. We're talking about observers at infinity. Yeah.
Yeah, so if I had to generalize this procedure, like this was for static black holes, right? If I had to generalize this to even stationary black holes, like
Yeah.
so there are cross terms, right? dt d5.
Yeah.
So if you go to Euclidean, there will be I factors of I. So what?
Yeah, rotating black holes are a little tricky because there is no such thing as the Euclidean version of a rotating black hole is a subtle thing because, as you say, there's going to be i's in the metric. You have two choices. You can either go to imaginary J, then the metric is real, or you can just be happy to use the complex metric. You are allowed to do a path integral on a complex metric. So I think the most direct way to think about it is that the Hartle-Hawking state on the rotating black hole is defined by a path integral on a complex manifold, on a complexified geometry with some i's in the metric. Yeah.
But in the rotating case, we lose this nice analogy. When we don't have a Hartle-Hawking state, we don't have this nice regularity that we have in Schwarzschild.
Yeah. Yeah, that's a caveat that actually applies here also. But yeah, there can be issues with this procedure, and the issues are bigger. Like, well, I'll have something to say about it in a minute. But they're worse with rotation. That's right. Yeah.
But this is the same problem that we would have had if we were in crustal coordinates, where the metric would become complex if we were to.
Well, sort of. I think the situation for rotating black holes is better. I think you can make sense of that path integral. I don't think that you could make sense of the Kruskal one, but I'm not totally sure. I'm not sure. I don't think you could.
So isn't this state like the Kruskal vacuum, and then you're tracing over degrees of freedom inside? Is that the correct word?
Yeah. the Hartle-Hawking vacuum is, well, I don't think there's such thing. I'm not sure. Is there such thing as a Kruskal vacuum? Is that a thing? I've heard that. Let's see. So, okay,
I mean, the lowest energy state as measured by Kruskal was in the.
But the Kruskal coordinate system is not static. So, I think what I'm calling the Hartle-Hawking state, I think some people call it Kruskal vacuum.
They agree.
But they agree, but the reason I'm not calling it Kruskal vacuum is I don't think there is a Kruskal vacuum because it's not a static state. So it's not a static metric. So like if you try to write down a state with no particles, it might have no particles at time 0, but then the metric is time dependent. It will create particles. So I think when people say the words Kruskal vacuum, they're referring to a state that's well, I think what they mean is the same as what I mean here, but I think it only has no particles according to someone on the horizon or something like that. There's some issue with what you exactly mean by Kruskal vacuum, but the terminology is just that it's the same as what I'm calling Hartle-Hawking. I had forgotten that people use those words, so that's why I'm confused, but I think that's what it means. Okay, so one thing we get out of this immediately, since this is a thermal field double state, that means that if we trace out half of it, we get the thermal state. That was the whole point of the thermal field double, was that it purifies the thermal state. So this means that if we define rho A, the reduced density matrix of just the right half of the black hole, if we define this in the Hartle-Hawking state, which is, remember the definition is trace over B of the total density matrix, which for a pure state is just the ket bra. And by our general discussion of thermal field doubles, this is the ensemble or the operator e to the minus 8 pi m h. That's the main result of this discussion. We've argued that the Euclidean path integral on the Euclidean Schwarzschild black hole prepares a state which is thermal in region A. That's the Hartle-Hawking state. Now I want to make a few comments about this. Okay, so this is thermal outside the black hole with respect to ordinary energy at infinity. Second comment is that this state describes a radiating black hole in equilibrium, thermal equilibrium, I should say. With its radiation, or just with radiation, I should say. So it's a black hole there's a hot gas. Well, not very hot, but it's a finite temperature gas outside the black hole. And this is an equilibrium state. So in the Hartle-Hawking state, there's a hot gas out here. Okay, so that means that there's thermal radiation both entering the black hole and exiting the black hole. Is really it's like gas in a box that you study in StatMech. You take the whole thing and you put it in the thermal ensemble. At no point did we say like only the outgoing modes are trace e to the minus beta h. We said all the whole thing is in the thermal ensemble e to the minus beta h, right? So that includes the ingoing modes. Yeah.
The thermal ensemble is going to include other black holes, right? Because they're going to be states produced by H.
No, we're doing, I should clarify here that everything I've described here is a quantum field theory calculation
Okay.
in a fixed geometry.
Okay.
Okay, we're going to come to quantum gravity, and sometimes the words are used interchangeably. So there's a state in quantum gravity, which is called the Hartle-Hawking state, which also involves doing a gravitational path integral. That is not what we're doing now. Right now we're just doing quantum field theory on a curved fixed background. Okay, next comment is really a caveat about this whole discussion. We've done this sort of formally, but there's a problem, which is that the thermal ensemble in infinite volume diverges. Okay, you can't really do this. If you want to actually do a calculation, you have to regulate it somehow, like by putting you have to like put the black hole in a box in order to define the state.
Did we have this problem before?
What?
Did we have this problem before with Unruly Space?
Yeah, I guess we did. I guess if you really try to, well, I think it's similar to that. I think we probably did have the problem there. We just glossed over it somehow. Yeah. And this is the caveat that, going back to the question about rotating black holes, this gets even worse with rotation, that when we have rotation, even in a box, the thermal ensemble can make no sense. The problem being that in order to have stuff in equilibrium with something that's rotating, it has to co-rotate with it. But if something's rotating very quickly, then, and you try to co-rotate it, the radiation tries to co-rotate with it, it's going to have to go faster than light or something, so it just doesn't make sense. So you get problems for defining states like this for rotating black holes, and things get extremely subtle, and we're not going to do that.
But they still have quantum radiation, right?
Yes. Yeah, there's still, well, yeah, the argument I'm giving doesn't really work for that case because of the way we're describing it, but the conclusion still holds, so. Yeah.
So if I want to think of this caveat in the language of entanglement, like are you saying that there are lots of short distance modes entangled and also there are a lot of long distance modes which are entangled, so it is doing both U
That's
and
right. Yes, it's an infrared problem.
But again, I think the same problem was there in Rindler space.
Yeah, I think that's right. I think the same problem was there in Rindler. The, it's a little. I think it's a little worse for. Let me see if I can if I can say why it's worse. I think it's worse for the black hole. The Minkowski state. Okay, the way I've described it, it sounds the same, but the vacuum state makes sense in Minkowski space. There is a vacuum state. It's perfectly stable. Everything is perfectly fine, even though there's a lot of infrared entanglement. The Hartle-Hawking state of a black hole in flat space actually does not exist. I think there is not such a state. At least when you couple, well, it might, maybe it's only a problem when you start worrying about if we're just doing quantum field theory, I think that state probably exists, but when we couple it to gravity, that state just doesn't exist because a hot gas has some energy density, and if you have energy density that's big enough, you make black holes. Okay, so if you really try to prepare a Hartle-Hawking state in flat space, and you couple it to gravity, the radiation itself is going to want to collapse into a black hole, and it just doesn't quite make sense. So you really have to regulate you really have to regulate where you're allowing the gas to be by putting it in the box.
So here, should I think of this divergence as because the size of null infinity is infinite?
The issue isn't null infinity, I think. It's just
because
spatial.
it's like the observer at null infinity is collecting all this radiation, right? But the size of the null infinity region is infinite.
Yeah, okay, that sounds about right. Yeah.
Because there is a constant flux and then he's collecting over infinite time. So that's the infinite.
Yeah, that's right. Yeah. Okay, the next comment is that according to an infalling observer, the Hartle-Hawking state is empty. At the horizon. How do I know that? Well, because at the horizon, you're really just working in the Minkowski vacuum. At the horizon, this is Rindler space, and the Hartle-Hawking state was designed in such a way that it's the thermal field double and therefore the Minkowski vacuum. So the fact that the Minkowski vacuum is empty for an inertial observer means that the Hartle-Hawking state is empty for an infalling observer near the horizon. So this fact is going to be crucial in a few minutes when we come to real black holes. Because what we're going to do when we talk about real black holes that form from gravitational collapse is to turn this logic around. Real black holes that form from collapse should be empty near the horizon. We'll come to it in a minute, but that's going to tell us that they have to have outgoing Hawking radiation. We'll come to that. Next comment. Well, as I've emphasized, Hartle-Hawking was a definition. It was a choice of state. There are other states on the eternal black hole which are different. Okay, so there's one called the Boulware vacuum, which is defined to be empty according to a fixed R observer.
One fixed R or all fixed Rs?
Any fixed R. So it's much like this. Sorry.
So like if you pick one RVM, do you do other RC particles?
All those people agree that there are no particles because they all have the same. They all have proper time t, the Schwarzschild t. So if they all agree about the definition of proper time, they'll all agree that there are no particles in a given state. So that's called the Boole vacuum. It's a choice of state. You can choose this state if you want. There's no Hawking radiation in this state. There's no thermal radiation whatsoever in this state. This you should think of as being like the Rindler vacuum. When we talked about Rindler space, we said that you could pick a vacuum for Rindler with no Rindler particles in it. And it's a very weird state because this state is singular on the horizon. That is, if you define this state, the Boole state, and then you try to jump into the black hole, you're going to encounter infinite stress energy when you hit the horizon. Okay, so it's better just not to talk about this state. I don't think it's physical. I don't think it makes any sense. We can define it as a state of the quantum field theory, but I think it just doesn't make any sense. It's no good. Okay. There's one more state that I want to mention, which is called the Unruly state. And this one is more interesting. So the Unruly state, or the Unruly vacuum, is defined to be thermal for outgoing and Boole for ingoing. So if I draw this, what this state looks like in the black hole, this has radiation coming out of the black hole on both sides. Actually, let's not talk about the other side. There are choices we'd have to make there. Okay, there's radiation coming out of the black hole, but there's nothing falling in. Now we should ask whether this state is singular or not. And this state is singular on the past horizon. Depending how we extend it, I think usually the way we define it, it's also singular here, but that won't really matter for us.
Stress energy is singular.
Yeah. Okay, so this state, remember when we were talking about entanglement and how the smooth, so quantum field theories are infinitely entangled at short distances. Okay, when you take, the point is that when you take these modes that want to be thermal and you force them to be in vacuum, you're destroying that short distance entanglement. So what you've done here is you've declared that there's no entanglement across the past horizon. And that's what makes it singular here. This is not an equilibrium state. You know, if we allow gravity to be turned on here, this black hole would evaporate because it's losing energy into the Hawking radiation. But and it's got this weird singularity. The reason that this is an interesting state is because this is actually the state that you get when black holes form by collapse. And the reason that's okay is they don't have a past horizon. Okay, so we're about to get to this, but the past horizon is not physical for a collapsing black hole, so they're allowed to be in this state. And that's what we're going to see in a minute. Questions? Yeah.
What decides what is and isn't a real state? You know, in many different spacetimes, we have different names for different types of states. What decides if something is a real state,
Well,
for lack of better terminology?
I mean, I think there is no one answer to that question, but what we should mean by that is one that actually could exist. Okay, so that means states that can form from some reasonable initial conditions, usually. Now, the Hartle-Hawking state on the eternal black hole is not real in that sense. Like, it's just a mathematical construction. As far as we know, there are no two-sided Schwarzschild black holes in the universe. But, well, there are different levels of real. Okay, the Hartle-Hawking state is at least a good, smooth state that you can use to do quantum mechanics in that space-time, whereas the Boole state is just sort of nonsense, even in this play universe. So I'm not sure. I'm not sure what you mean exactly, but does that answer it?
Yeah, I mean, Boulevard is also singular in the future horizon too, right?
Yeah.
So, I mean, that would not fit well with things like the equivalence principle of black holes.
Yeah, that's right. I mean, it's always a matter of what you're going to apply it to. Okay, so if you're just going to do quantum field theory in the exterior region, you're free to use the Boole state. That's something you could do. And if you stay in the outside region, that's okay. And similarly, if you do the Unruly state, but you stay away from the past horizon, that's okay. Yeah.
Your answer about initial conditions, I think, was what I was asking.
Okay. Cool.
I have a,
Yeah.
so like the Hartle-Hawking state appears thermal for an asymptotic inertial observer, right? That's what.
Yeah.
So, like, what happens to an asymptotic accelerated observer? What state would he see?
I don't know. I guess it wouldn't be terribly hard to calculate. But if you're wondering if it would cancel off the Hawking radiation,
Yeah, maybe something.
then I can tell you that won't happen, because how would we calculate it? See, an accelerating observer will be restricted to a patch like this.
Yeah.
Okay, so we could define a reduced density matrix on that region,
Yeah.
and it's going to be mixed, and it's going to have stuff in it. Like there's no way it's going to be the vacuum with respect to this boost.
Except unless it's like an infalling observer that's infinitely far away, then we would have said that it would.
Well, I think Jivan was asking about this state here. Is that right?
Yeah.
Yeah.
I mean, how do we think of this in the language of entanglement?
Well, I'm about to say something about entanglement. I'm not sure what you mean, but let me see if this answers it.
Okay.
Okay, so before we go to real black holes, the last thing I want to describe is just sort of how to think about the Hartle-Hawking state a little bit. And this is going to necessarily be slightly vague, so forgive me for that, but I want to tell you how I think about it. Okay, so well, not just how I think about it, it's how everyone thinks about it. Okay, so So you should think about this state as having a lot of entangled stuff across the horizon. What I'm drawing there is an entangled pair. I don't mean that literally. What I mean literally is the Hartle-Hawking state. We already gave the literal definition. But roughly speaking, there's entanglement across the horizon in this way. And the blue guys are entangled with the blue. These green ones are entangled with the green. And similarly, there's entanglement along the past horizon. So there's entanglement between these guys. I'm going to run out of colors, but there's entanglement on those. And similarly on the other horizons on the other side. Okay, I'm not going to try to draw more colors, but all this stuff is entangled. Now,
But just saying that, like, in the Hartle-Hawking state, since it's a Manifold double state in the various terms, you have like eigenstates of the Hamiltonian on one side.
yeah, that's right. That's right.
The Hamiltonian on the other side.
That's right. But the point I want to make is that this is really happening in a region near the horizon, like that. I mean, it's not that it disappears immediately, but it's that most of the thermal gas is in this region that's hugging the horizon. Most of the thermal gas is inside the dotted lines. Now, it gradually, a tail extends out all the way. There's a little bit of entangled stuff here. It's entangled with something deep over there. There's very little of that. Most of it's happening very close to this horizon, close to the black hole. And the reason for that, we can understand that just directly from the thermal field double state. So in Euclidean, stuff near the origin has a small charge with respect to rotations, Euclidean rotation. So if I draw the Euclidean thing, where this is r equals 2m, and tau goes around, then clearly if I put an object here, it's going to have very small, well, an object, if I take that object there, it'll have a small angular momentum. If I put something out here, it'll have a large angular momentum. Okay, so the charges associated to the modes near the origin are very tiny. The charges associated to the stuff out here are very large. And that means when we look at the thermal ensemble, it's going to be dominated by stuff near the origin. Okay, so in this thermal field double type state, this is just the maximally entangled state near the origin. And then if you go far away from the origin, it's just unoccupied. Okay. So very roughly speaking, you can kind of think of this as the very entangled state near the origin, and then quickly dying off and just being unoccupied when you get away from the origin. So that's where this picture came from. Good. Okay, so I want to finish up. Oh, go ahead.
I can ask you later.
No, go ahead.
This explains why they die off as you go farther away, but how does this why is the Hartle-Hawking state corresponding to entanglement across the horizon? What's that even?
Well, the Hartle-Hawking state is the thermal field double. So that's entanglement. That's what that is. That's what I mean when I say that it's entanglement across the horizon, because this is like in A and this is in B. So it's stuff that's entangled across the two sides. Now, what I have not explained was why stuff going this way was entangled with stuff going this way. A lot of times people draw this picture wrong. They draw it like this, and that's not correct. You have to sort of think carefully about what this mode sum really looks like in order to get the picture that I drew here, but I wasn't going to go through that. Yeah.
Why does it look like a dimensionally entangled state near the origin?
Because near the origin, the boost charges are very small, so this exponent just goes. This is a boost charge showing up, or in this case, a regular energy. Sorry, for Rindler, it's a boost charge. In this case, it's just the ordinary energy showing up here. These energies are very small for stuff near the origin. I should have mentioned, physically, this is redshift. Okay, the stuff near the origin is very redshifted. Okay, so the stuff near the origin has very low energy as measured from infinity. And therefore is basically unsuppressed in the thermal sum. And as you get closer and closer to the origin, it's more and more redshifted. So it's easier and easier for it to get excited in the Hartle-Hawking state. Was there another question?
I did, but
Yeah.
it was exactly the redshift.
Ah, good. Okay. Yeah.
So you said the entanglement is between states on A and B, so does it mean the ingoing radiation is part of, is defined on B?
No, the ingoing radiation is this here is the ingoing radiation, so that's still part of A.
Okay.
But the ingoing radiation on this side is going to end up entangled with the outgoing radiation. I mean, these things keep going, so this keeps going, and so the ingoing radiation on this side is entangled with the outgoing radiation on the other side.
So for the radiation above, unlike for the blue and green arrows, I think the ingoing are those just inside the horizon.
Sorry, say again?
So for the blue and green arrows, the arrows inside the horizon are the ingoing radiation.
Well, they're ingoing from the left.
Okay.
See, these modes came from back here somewhere.
Okay, so they cross the region B.
Yeah. Once they're in here, I don't think I would just call them sort of trapped. They're not neither ingoing nor outgoing. But yeah, they came from the ingoing modes on the left. I mean, I'm drawing this in space-time. Of course, entanglement is something that happens in space. In other words, we could just fix time 0, and I'm saying that this mode is entangled with this mode, and that mode is entangled with that mode. But often, well, I just drew them in space-time because if we happen to be an observer falling through, say like this, then it's more useful to think about them as entangled across the horizon that we're actually crossing. Yeah.
Now, people sometimes talk about this picture as like related to pair production across the horizon.
Yeah, sometimes people say Hawking radiation is pair production across the horizon.
Does that make any sense?
I think it's not a bad analogy.
How do we think about it that way? Or how do we see that in this picture?
I don't know. I wouldn't try to take that analogy too seriously, but you know, what's happening is that you have some entangled pairs, and the curvature of the space-time is allowing one to escape. You know, if this were just Minkowski,
Yeah.
of course, this wouldn't really be a physical effect for an inertial observer. But the curvature is sort of tearing them apart. It's allowing one to escape. I think it's
But in what sense should we
not
think
bad
of
to
these
say that it's
as,
pair
like-
production. What?
In what sense should we think of these as like virtual particles that are torn apart or something like that? Or does that?
I think it's not a terrible analogy. I mean, these are virtual particles in the sense that these are just, when they're near the horizon, well, in curved space, I'm not sure what's a particle and what's a virtual particle, because it depends on the observer who's measuring it. People have different idea of what a particle is in curved space. But there's some modes. If you think of a mode as a virtual particle, there's some modes. Those modes are entangled, and then one of them, this one escapes to infinity, becomes observable. So I think, I don't know. I know some people really hate this analogy, but I think it's okay. There's even, I think you can even make it into a computational method. There's a way of thinking of Hawking radiation as a tunneling process. And then the analogy is even closer.
I mean, since these are like maximally entangled near the origin, so can we think of each mode of each frequency as a bell pair?
Yeah, near the horizon, yeah.
Yeah, near the horizon.
Yeah. But these are modes, of course. The modes are perfect bell pairs. What I'm drawing here are not modes. They'd have to be plane wave. They'd have to be sort of plane wavy to be in a bell pair. What I'm drawing are more like wave packets that are supported on certain modes. So it's not literally a bell pair, I think. It's pretty close, though. I think it's close.
So if we think about pair production, then it means the particle doesn't always exist, like along all the spatial slices. So it's possible that you cannot extend its word line backward all the way to region B.
Yeah, that's a little tricky in curved space because whether it exists or not is sort of observer dependent. I think when we talk about the evaporating black hole, it's pretty clear that those modes were created. The Hawking radiation of an evaporating black hole is something that's created. The modes, the particles weren't real before they came out. Yeah, so I think pair creation is not bad. Okay, we're going to stop here. Are there any more questions? You can hang out.